Yeah, it's a good time. So let's start the third Extreme Universe public online colloquium. Usually in our public colloquium, we invite only one speaker from the outside of the Extreme Universe collaboration, but this time is very special. It's a joint seminar by Tasaki-san and Oshikawa-san. Oshikawa-san is just a member of the Extreme Universe collaboration. But anyway, as you know, Tasaki-san and Oshikawa-san are the world-leading researcher in the theoretical statistical mechanics and yeah, mathematical physics associated with quantum many body problems. And actually, they made a very fundamental and important contribution to the foundation of currently hot research topics such as SPT physics, generalization of Lipschitz-Mathe theorem, and so, for example, the measurement-based kind of computation, and so on. So today, we are very excited to hear talks associated with a series of theoretical developments starting from the Haldane conjecture directly from Tasaki-san and Oshikawa-san. The beginning of the Haldane conjecture is a just spin chain problem, but subsequent advancement developments have evolved various research fields, not only in the condensed matter physics, but also quantum information and high energy physics. So in this sense, I believe that the talks by Tasaki-san and Oshikawa-san provide very illustrate some intrinsic thrills involved in theoretical physics across some generations and background research fields. And additionally, here I would like to comment on the photo in the poster of the this colloquium, which shows Professor Ian Affleck between the Tasaki-san and Oshikawa-san. Yeah, you can see in the Tasaki-san's slide. Of course, Professor Affleck is one of giants in theoretical physics, and actually he made a very great contribution to so many aspects of theoretical physics. So of course, you know the equality model and like a condensed matter application of conformal field theory and so on. But it's very sad. But yeah, he just passed away the last October. But however, his remarkable works uh, still inspiring many physicists, including myself, and so far and so on. So in this sense, this moment provide us some valuable opportunity to revisit the physics associated with a Haldane conjecture problem. And I hope it also resonate with a younger generation uh, here in audiences. Anyway, let's enjoy Tasaki-san's talk, the first part. So Tasaki-san, could you start?
Thank you very much for kind introduction. So I'd like to first thank the organizers, especially Okunishi-san, for inviting me and for arranging this joint colloquium with Masaki Yoshikawa. I'm excited about this. Okay, so as Okunishi-san said, this talk is dedicated to the memory of Ian Affleck, who passed away last year. Okay. Anyway, let me start by saying something extreme universe. Okay, so quantum mechanics is surprising. I think you agree. And I would say it's surprising in all directions. So many directions. So please fill in your favorite topics here. And I want to stress that it's surprising not only when applied to microscopic physics, but it's still surprising when applied to macroscopic physics. For example, in these days, we have learned that quantum mechanics leads to various non-trivial quantum phases of matter, which can be observed which can be realized in actual condensed matter systems. So today I'm going to discuss one of them from a mathematical physics point of view. Okay, so this is my content. So part one is basically review about Haldane gap and everything. And a good reference for this part one is, I'm sorry, it's my own book published some years ago from Springer. It's entitled Physics and Mathematics of Quantum Many-Body Systems. And it comes with a beautiful illustration by Mario Kazaki. Okay. Okay, so let me start by discussing a very simple example of a system with only two spins. And first of all, classical spin. Classical spin is nothing but a three-dimensional vector with a fixed size. And if you have two spins, and if you have this energy, so ferromagnetic interaction, then it's easy to find the ground state. You want to minimize this, so the only thing you have to do is to let two spins point in the same direction. But it can be pointing in any direction, so there are infinitely many ground states. And somebody should mute. Okay. And when you have antiferromagnetic interaction, then it's almost the same. Then the two spins should point in the opposite direction, but then they can point in any direction. So again, you have infinitely many ground states. Okay, quantum spin is basically operators that satisfy this familiar commutation relation for angular momenta, and this is spin quantum number. So let's consider the simplest case with spin 1/2. Okay. And then this is ferromagnetic interaction, and you know how to minimize this by adding two spin 1/2. It's the problem addition of angular momenta, and you see that this Hamiltonian is minimized by something called spin triplet. So these three guys minimize this Hamiltonian, but of course, you can consider any linear combination of these states. So there are infinitely many ground states in this case. But if you consider antiferromagnetic interaction in this quantum case, then you know that the answer is there is only one state that minimizes this Hamiltonian. That's something called spin singlet. Of course, you know. So in this case, we have unique rotationally invariant ground states. So if you compare these four cases, then this antiferromagnetic interaction with quantum spins is something different than others. So it's more interesting than others. So that's why we're going to consider quantum antiferromagnetic chain. And also this Heisenberg chain is, I would say, one of the most standard and realistic models, even realistic. It can be almost realized experimentally, models of quantum many-body system. Now we have a chain, and it can be an infinite chain or a finite long chain. I will be more specific later. And on each side, you have spin. So Sj denotes spin on side J, and this is the Hamiltonian. So we simply have this inner product form for every bond. Okay, and S is spin quantum number. So this is a very good model, and the only model parameter is this spin quantum number S. And we are interested in the property of the ground state and low energy excitation. And as you may know, back in early 1980s, Duncan Haldane made a fundamental discovery on this subject. He argued, he discovered that low energy properties of this model depends on whether this spin quantum number S is a half-order integer like 1/2, 3/2, or integer like 1, 2. And first of all, he argued that if S is a half-order integer, then the model has a unique gapless ground state. Okay, there's a ground state, and there's no gap in bunch of excited states. And people were not surprised about this because they already knew about the beta and the solution for the spin 1/2 chain. But for integer S, Haldane argued that the model has a unique gapped ground state. To be precise, the model has a unique ground state accompanied by a non-zero energy gap immediately above the ground state energy. So this is a ground state energy, and there is a gap. And if you increase the system size, this gap doesn't close. It always stays the same. And people were surprised, or people did not believe in this because this assertion was so different than the belief at that time. And so actually Haldane's first paper was rejected by 3 journals and never published. But anyway, many things happened, and finally Haldane, of course, got Nobel Prize mainly about this. But I'm a mathematical physicist, so from a mathematical point of view, this is still a conjecture. Of course, we believe in this. Everybody believe in this, but mathematically, this still remains as a conjecture. Okay. Now, so we are interested in this integer spins, and the smallest positive integer is 1. So in this talk, I will focus on spin 1 system. So, of course, for a single spin, spin 1 operator are simply these 3 by 3 matrices, and these are standard basis states, and they are, again, state of SC. And if we want to consider spin chain, in case of spin chain, for each site J, we have Sj, which is a copy of S. And as I said, this is a very standard model, antiferromagnetic Heisenberg chain, and it is expected to have a unique gapped ground state. Okay, but suppose that you are very much interested in having a unique gapped ground state. Suppose that was your goal. Then you don't have to consider this such a difficult Hamiltonian. It is sufficient to consider this simple Hamiltonian. Now, what is this? This is simply the sum of Sz squared, no interaction between spins. And Sz is this operator or this one. So then it's very, very easy to minimize this thing, right? From this, you immediately find that the ground state obtained if you just have a bunch of zeros. So ground state looks like 0, 0, 0, 0, 0, 0, 0. Okay, and if you want to if you want an excited state, then you simply replace one of zeros by plus or minus. Then you get energy 1. Okay, so so in this case, ground state energy is 0, and the first excited state is 1. Ground state is unique. So you have a unique gap ground state. So, but is this worth a Nobel Prize? I don't think so. So there must be some essential difference between the unique gap ground state in this case and in this case. To see this difference, let's look at an interpolating model, this one. So S is a model parameter that runs between 0 and 1. And if S equals 0, then this vanishes and you only have this. So this is this trivial Hamiltonian. When S equals 1, then this vanishes and this is equal to this Heisenberg Hamiltonian. So let's see what does this Hamiltonian do. And of course, you cannot solve this. So let's do numerical plot. And this was done by my young friend Emil. And so this is a plot. So this is S, model parameter. And this is the energy gap, the difference between the ground state energy and the first excited energy. And first of all, look at here. Here you have 1, but this is something we already know, right? So this model has energy gap 1. So this is trivial gap for this trivial system. And here you see that you observe that this is a Heisenberg model, and it seems, oh, well, I didn't say this. So this is a numerical plot of energy gap for finite, of course, finite chain with periodic boundary condition from size 4, 6, finally to 18. And this is sort of going down, and it looks like it's converging to somewhere here. And actually, everybody believes that this converges to somebody like 0.41, and this is the Haldane gap. But look here, in the middle, it's sort of decreasing, and it looks like it's going to 0. So it looks like there is a gapless point here. So is there a phase transition between the two models? It really looks like. But, there are no broken symmetries here or here. So this is the phase diagram for this case. So here we have trivial model. So probably this should be called the trivial phase. Here we have Heisenberg model with the Haldane gap. So probably this should be called Haldane phase. But what is this? What is this phase transition? So we have critical point, but what is this phase transition? What are these phases? You already see, but this is characterized by unique gap ground state, this one too. No symmetry breaking. So how can you distinguish between these two phases? So there was one thought back from 1987 by Ian Affleck, Tom Kennedy, Elliot Leap, and myself. And among other things, we sort of argue that the ground state of the Heisenberg chain, in a sense, resembles something that we call the valence-bond solid state, VBS state. Sometimes this is called the AKLT state. And this is a state. represented diagrammatically. So let me explain what this is. Okay. First of all, we are dealing with spin 1 system. Okay. I only deal with spin 1 system, but this black dot represents a spin 1/2. Okay. Now, these two black dots are connected by this line segment. It denotes a spin singlet formed by these two spins. So to be more accurate, if this spin is 1, this is spin 2, then this should be 1, 2, 1, 2. Okay, so this is your familiar spin singlet. Okay, finally, this one. So you have two spin 1/2s here, and this dotted oval represents symmetrization of two spin 1/2s. Okay, so if this one is this, if this one is this, then this whole thing represents this. So it's symmetrized. And as you know, this symmetrized state is always a spin triplet. Okay, so it has spin 1. So this dotted oval is basically a projection operator from the state of two spin 1/2s into a state of a single spin 1. Okay, so here I started from sort of a doubled system of spin 1/2, but we applied these projection operators. So on each side I have spin 1, spin 1. So this is a state of spin 1. Okay, and let me emphasize that here you have a singlet pair. And of course, in this spin singlet, this spin 1 and spin 2 are highly entangled. So in this state, there are bunch of entanglements going on. Okay. Oh, and let me also mention that this VBS state or the AKLT state is a prototypical example of a matrix product state, MPS. But we didn't realize that because there were no notion of MPS at this time. And let me also remark that we did the higher dimensional version of VBS state, and I believe it was the first example of tensor network state. Okay, and you're not surprised if I say we can compute exact correlation function of this because it's MPS. But anyway, we discovered that we can compute correlation functions exactly, and these 2-point functions exhibit exponential decay. Okay, and we also found that this state is the exact unique gap ground state of some Hamiltonian, which is nowadays called a parent Hamiltonian, and which is a frustration-free Hamiltonian anyway, which is this. So anyway, this is an artificial Hamiltonian. We wanted to study the model, the Heisenberg antiferromagnet, but we had to add this term. Okay. So that was what we found in 1987, and so we did not justify Haldane's conjecture, right? Haldane's conjecture was about the Heisenberg model. So but we found that if you allow me to add this term, then anyway, what Haldane said was realized in this case. But actually, we found more than Haldane predicted. We found some exotic properties, at least exotic back in 1987, properties of these VBS states. And first of all, so this is the VBS state represented diagrammatically. It looks like a very simple state. But as I said, this is a state of spin 1. Spin 1 is always. So you can, of course, expand this in the standard plus minus 0 basis of spin 1. So if you do that, of course, I didn't write down anything, but you get a bunch of basis states and coefficient, you get a huge sum. But if you look at the term that appears in this expansion, actually not all basis states appear. And here's already a punchline. If you look at the expansion if you look at the basis states that appear in this expansion, there is a strict rule. So if you forget it, if you don't look at zeros, then if you only look at plus and minus, then plus minus plus minus plus minus completely alternates. Okay, so I would say you can say that there is a hidden antiferromagnetic order. Okay, of course, there's no real antiferromagnetic order. Correlation functions decay exponentially. Okay, there's no real order, but if you expand, you see this kind of hidden order. And Janice and Ramos pointed out that you can measure this kind of order by looking at this kind of non-local correlation function. Okay. The second exotic property was found if you consider ground state on open chains. So we found that for a periodic finite chain or infinite chain, the ground state of this Hamiltonian is unique and it has a gap. But if you consider the same Hamiltonian on open chain with two ends, then we found that there are four ground states rather than one. But it's easy to understand this diagrammatically. So as I said, and here, this is spin one, so you have to have two spin one halves, right? And these spin one halves are, forming singlet pair with neighboring guys, and this y guy is forming spin singlet pair with this one, but this one cannot form any pair with anybody else, so it's kind of free, and this one too. So this leads to emergent spin one half degrees, emergent spin one half degrees of freedom at two ends, and that results in this fourfold degeneracy. Okay, so these were what we found for this artificial exactly solvable in the sense that you can write down the ground state model, but later it was pointed out that these exotic properties were not only for the BBS model, but they are universal features that characterize the Haldane phase. Of course, this is not rigorous, but this is just a picture. Okay, so now at this point, people realize that there is something like phase transition. Okay, and it's hard to distinguish between these two phases. But in this phase, you have these exotic things: hidden antiferromagnetic order and emergent spin one half. Okay, this was discovered by Tom Kennedy by using numerical simulation, but it was also observed experimentally, and nothing like that, nothing weird in this trivial phase. Okay, so this is nice, but still strange. Why do you have this strange exotic behavior here? So here is one more thought. So back in 1992, Tom Kennedy and myself proposed non-local unitary, defined a non-local unitary transformation, which we wrote down much more complicated, messy formula. But then young Masaki Yoshikawa came and found that it can be rewritten in this compact, beautiful form. Okay. And anyway, what we observed is the following. So this is the interpolating model we have been discussing. Okay. And if you apply this unitary transformation, non-local unitary transformation to this guy, then it turns into this new Hamiltonian. It looks totally different. And look, it's more or less ferromagnetic here. You have this one is weird. Okay. And also the symmetry is different. This Hamiltonian is invariant under any rotation about z-axis. Okay. So it has a continuous U1 symmetry. But this one has much less symmetry. Then actually it only has discrete symmetry. It's invariant under Z2 cross Z2 transformation. That is the pi rotations about X, Y, or Z. Okay, but you have three, but pi rotation about Z-axis can be obtained by rotating about X-axis, pi, and also pi rotating about Y-axis. Okay, so that's why it's Z2 cross Z2. Anyway, it only has discrete symmetry. Okay, and we found something. Yeah, let's go to the next page. So we found that the Haldane phase is mapped by this non-local unitary transformation into a ferromagnetic phase with full spontaneous breakdown of the discrete Z2 cross Z2 symmetry. This is rigorous only for this solvable VBS model. But anyway, we observed this. So we sort of believe that this happens for all the way in the whole Haldane phase. Okay? And this picture that we call the hidden Z2 cross Z2 symmetry breaking is rather nice because it explains all these exotic properties of the Haldane phase. Okay? First of all, so here we have this spontaneous symmetry breaking of discrete symmetry. Then it's very natural to have a gap. Here we have ferromagnetic order. Then this is converted into hidden antiferromagnetic order in the original system. And finally, we have spontaneous breakdown of Z2 cross Z2 symmetry. So we should have four ground state. And this is mapped to fourfold near degeneracy on open chains. Okay, so this was a nice picture. And as a mathematical physicist, I want to say something about the rigorous proofs. And this unitary became basis for some rigorous proofs for some nice theorems like rigorous perturbation around the BBS model and so on. But it was not useful for some very useful, important purpose. Okay, so look at this thing. So this is another interpolating Hamiltonian. This looks like the previous HS, but this is slightly different. This Hamiltonian interpolates between the solvable AKLT BBS model and this trivial model. And we know that this is in Haldane phase. We rigorously know this is in Haldane phase, and this is trivial. Okay, so if you interpolate between two of them, it's quite likely that there is a phase transition in between them. So we wanted to prove this, and okay, if you apply unitary non-local unitary, then you can prove the existence of phase transition because this one, after transform in this dual world, this one has 4-4 degenerate ground state. This one exhibits symmetry breaking, and this one is trivial. Okay, so there is a phase transition. It's rigorous in the dual world of this interpolating Hamiltonian. But if you go back to the original, that's weird, but we still could not prove that there was phase transition. Okay, so anyway, that was mathematical physics, but we liked this picture, and once we thought this could be the final answer, we discussed with Masaki this, but there were some puzzles to be solved, and we were not sure if this was the final answer. And actually, this was not the final answer. We had to wait for a long time to learn the final answer from Gu and Wen back in 2009, and also by Paul Manterno, Belk, and Masaki Yoshikawa. Actually, their paper appeared in 2009, and their final answer was that these two phases should be understood as different symmetry-protected topological phases. Okay, and they say that there is always a phase transition if the interpolating Hamiltonian that connects here and here have one of the following symmetries: time reversal, Z2 cross Z2 that I already explained, or bond-centered inversion. And there is fourth symmetry discovered by Yohei Fuji, and actually this is important for me. Okay. Anyway, so the picture, the rough picture is the following. So suppose this is H0, this is H1. And suppose that this plane represents a model with one of these symmetry, nice symmetry. Okay, so if you want to connect H0 and H1 within this plane, okay, then no matter how you do that, I'm still in the plane, and then you hit this ring to go in order to go from H0 to H. And on this ring, you have gapless models. So if you are on this plane, no matter what you do, you have to go through this gapless mode. So you always have a phase transition. But if you're out of this plane, that means you don't respect this symmetry, then you can go from here to here without passing through gapless model or anything. So you can just connect from here to here by going through models with unique gapped ground state continuously. In this case, there's no phase transition. Okay, this was a picture of symmetry-protected topological phases. And the picture of SPT comes with the notion of topological indices. And according to the theory, these two phases should be distinguished by a topological index, which takes value in the second group cohomology of the symmetry group. But don't worry, usually this is very simple. In many cases, this is just Z2, 1 minus 1. And this topological index should be defined for a unique gap ground state on the infinite chain, of course, and is invariant under smooth modification of the model with unique gap ground state with necessary symmetry. Okay, and such an index was first defined for a class of states called injective matrix product states by Paul Manterno, Belk, and Oshikawa. And also, this is the starting point of all these indices. And then I myself defined index not for matrix product states, but rather general unique gap ground states, but I have to impose U1 invariance. And the final answer came from Yoshiko Ogata. Actually, the paper appeared in 2018, slightly after mine. And this is the final answer, and she was able to define topological index for unique gap ground state in one-dimensional quantum spin chains that can host non-trivial SPT phases. And so the indices or index was defined. And if you compute this index for, say, the trivial model for here, then you get trivial value 1. And if you compute this, again, you can compute this for the VBS model, the AKLT model, and then you get -1, okay, here. Okay, so that was the topological index. Okay, so this is the end of my part 1, which was sort of review. And so I reviewed Haldane gap and SPT phases before the summer, before last summer, when I did something. Okay, so at this point, we had rather nice general picture about SPT phases from Gu and Wen and Pullman, Turner, Belk, and Oshikawa. And we have well-defined indices and index theorem mainly by Yoshiko Ogata. And also there wasn't good example. So BBS model or the KLT model provides a rigorous example of the Haldane gap and also topologically non-trivial ground state. Okay, and as a byproduct of this index theorem, now we have this mathematical results for the existence of a phase transition. So this is the model that interpolates between the solvable AKLT VBS model and the trivial model. And we could prove by using our index theorem that this model undergoes a phase transition at certain s in between 0 and 1. Okay, but I want to stress that at this moment, nothing rigorous was proved about the antiferromagnetic Heisenberg chain. That was our starting point. Okay, and this will be the topic of the second part. But any questions for the moment? Can I go on? Okay, so let me go to part 2. And so the goal of part 2 is the following. So this is the Heisenberg antiferromagnetic chain. I consider only spin 1. And there are 2 conjectures. One is, of course, the Haldane conjecture. It has a unique gap ground state. And number 2, it belongs to a non-trivial SPT phase. Okay. Now, of course, we want to solve both of them. But it looks like Haldane conjecture is very difficult. So for the moment, let's assume Haldane conjecture and try to prove this one, the conjecture number 2. Okay. And in fact, I spent a long time, many years, thinking about this. And I thought that this was a very difficult problem that required us to develop new mathematical techniques. But surprisingly, I discovered that I discovered that proof was rather elementary if you find the correct setting to work on. Okay, so this is a paper. Okay, so now part 2 is a little bit more technical. So anyway, in the first part of part 2, I want to discuss my elementary index theorem. Okay, and this index was defined in my paper back in 2018. And actually, in my papers, I basically work on infinite system and directly define my index for the ground state of the infinite system. But here, I don't want to go into discussion of infinite system. So I will only consider finite system and take infinite volume limit when necessary. Okay, so I consider general spin 1 Hamiltonian. Okay, so this is a bulk part, and I consider finite chain with 2L plus 1 size like this, and I can have some boundary conditions near boundary. Okay, and here are my requirements on this Hamiltonian. I first require that U1 invariant. It means that it's invariant under any rotation about the z-axis. Okay, this is SC total. These are rotation operators. I also assume that it's invariant under site-centered inversion. Okay, so you fix this and you simply switch like this, and so this unitary does this. This inversion, and I assume that this Hamiltonian is invariant. And finally, I assume that this Hamiltonian has a unique gap ground state, and this energy gap is lower bounded by delta E uniformly, which is a constant independent of L. Okay. Under this assumption, I prove that there is a well-defined index for the infinite system, and which takes value between whose value is either 1 or -1. And this index is invariant under a continuous modification of the ground state that satisfies this symmetry. Okay. And what is this index? Actually, it's very simple. This is my definition. So only one line, or actually I need only 3 lines. Okay, so this is something called a twist operator that goes back to these people. And this is basically, as you see, this is basically the rotation operator about z-axis. But this is rotation angle. Rotation angle depends on the site. And as you see, in this region, rotation angle is 0, so it's not, doesn't do anything. And since this is integer spin, 2 pi rotation is the same as nothing. Okay, so it doesn't do anything here. So it does something non-trivial in this region, where rotation angle gradually increases from 0 to 2 pi. Okay, so this is a rotation, but rotation angle changes slightly. So this is a twist, gentle twist. Okay, and my index is very simple. It's basically the ground state expectation value of this unitary operator. Okay, and then I take the infinite volume limit and then the limit in which alpha goes to 0. And I can prove that this is either 1 or -1, and this is topological. I mean, this is invariant under continuous modification. Okay, let's look at some examples. So trivial model, this is very simple. You know that the ground state is this. So if you want to compute this expectation value, you know, this is 0. So this is e to z, 0 is 1. So you get this 1 here. And as for VBS state, this is less trivial. But if you look at this picture of plus and minus sandwiched by 0, then you can rather easily convince yourself, I'm not going to explain, but this becomes -1. And in this case, you can show that this index is -1. Actually, all this goes back to the observation by Nakamura and Todo that this kind of expectation value can distinguish between different SPT phases. Okay, and now, as a byproduct of this observation, I could prove in this 2018 paper the existence of a ground state phase transition in this interpolating model. In this interpolate, as I said, the solvable AKLT, the VBS model, and the trivial model. Okay, and let me prove this theorem. But good news is that the proof only takes 3 slides. Okay, lemma number 1, U1 invariance and the existence of unit gap ground state imply this inequality. Okay, first of all, this is unitary, so the expectation value, of course, satisfies this. So this is trivial. Non-trivial one is this inequality here. Okay, and so, and as I didn't say this, but alpha is positive. Okay, so suppose that alpha is positive but very small. Then this guy is small, like this guy is very close to 1, like 0.9 or something. And then this inequality means that this expectation value lives, this is a complex plane, lives in this ring-shaped region. So this is 1, and of course this is, say, 0.9. So it lives in this ring-shaped region. It's topologically non-trivial. So, okay, anyway, so this is what this means. So how do you prove this? It's quite easy. So let's apply this unitary twist operator to the ground state and call the result psi. Okay, this is it. And we want to examine the energy expectation value of this state psi and look at the difference between the ground state energy. And I say that it's small. It's upper bounded by constant, some constant times alpha. So when alpha is small, this is very, very small. Why? Well, it's not hard to see. So this theta rotation angle depends on J, but suppose that it didn't. So it's a constant rotation. Then in this case, since the Hamiltonian is rotation invariant, if this was the case, then of course energy doesn't change. So this is 0. Okay. So, but in this case, this is not a constant, but it changes only gradually. Only gradually. This means that energy increase per bond is proportional to alpha squared. I think you can easily convince yourself about this. And also the number of these twisted bonds is proportional to alpha inverse. So if you multiply them, you get this. Okay. So what does this mean? Well, this says that the energy expectation value of psi is very close to the ground state energy. Does this mean that psi is a low energy excited state? Never, never. Because we assume that there is a there is a gap. So this is a ground state energy, and there must be a gap. Okay. So if this C alpha is very small, I mean, if it is small compared with this gap, then this is possible only when psi itself is very, very close to the ground state. Okay? So with this and the existence of gap, if you do undergraduate calculation, you can easily show this lower bound, which says that this inner product is almost 1. And if you recall that this inner product is nothing but this, then this is this. Okay, so it was easy. Okay, so this is lemma number 1. Lemma number 2 is much easier. This says that invariance under site-centered inversion says that this expectation value we are looking at is real. Okay, how do you see this? First of all, I look at the inversion of the twist operator. So this is a twist operator. I apply this inversion. So then this j becomes minus j. Okay. Now, since this is integer spin, 2 pi s doesn't do anything. So you can add 2 pi here. And also, I just brought this minus here. Okay. Then I argue that this 2 pi minus this thing, this guy is equal to theta j. Why? Well, this explains. So this is theta j. It goes like this, and this is the center. And if you first of all do this inversion, and then this becomes this, and then you put minus sign in front, then this becomes like this. And finally, you add 2 pi to this to shift it like this, then you get this. Okay. So this guy is equal to this. So this one then is almost this one, but doesn't have this minus sign. So it means that this is equal to U Dagar. Okay, the rest is easy. Now I assume that the Hamiltonian is invariant under this inversion, and then this inversion implies invariance implies that the unique ground state is also invariant. So this expectation value is of course equal to this one. And now if you look at this part, this is equal to U Dagar. So it means that this is equal to this expectation value star. Okay. So this guy is equal to its own complex conjugate. So we have seen that it's real. Good. Now, number 3. Now, we have these two lemmas. Okay. The first lemma says that this expectation value lives in this ring-shaped region. The second lemma says that it takes real value. So both of them together imply that this can live only in this region or this region. Okay, so they can live on these two intervals which are disconnected. Quite topological. Okay, so now I can. So this is a bit different definition of my index. But now what I do is that I ask whether this expectation value in the infinite volume limit lives here or here. Okay, if it lives here, the index is +1. If it lives here, index is -1. Okay. Then why is this topological? Well, it's quite easy. You know, suppose that your index was -1. It means that you are here. Okay, and for some sufficiently small value of alpha. Okay, and then you change your infinite volume ground state continuously. Okay, by a continuous change, of course, it can move, but you know, it can never jump from here to here. It means it's discontinuous. Okay, so from the continuity, you can see that for finite but small alpha, this sign never changes. Okay, so this proves that the index is a topological invariant. Okay, and we also see that this can be written like this, but again, this is quite easy because you know, for sufficiently small alpha, it's somewhere here. But if your alpha becomes smaller and smaller, and this becomes closer and closer to 1, so this is finally forced to come here or come here. Okay, 1 or -1. Okay, that was the index theorem. Okay, so now I want to go to my main theorem, and this is about the antiferromagnetic Heisenberg model, as I promised. And here I must consider finite system. Okay, so I consider the antiferromagnetic Heisenberg model on this finite chain, finite open chain with 2L plus 1 sites. So this is my Hamiltonian. This is a standard Heisenberg Hamiltonian, and I add this boundary magnetic field. And I let this, the ground state and the first excited energy. This is my assumption. This is the assumption that I must make for the moment. Okay. And of course, this is highly non-trivial and unproven. This is basically the Haldane conjecture. I assume that there are constants H, delta E, and L0, L naught, such that this energy gap is lower bounded uniformly for any L. Okay. And of course, this is expected to be valid with this Haldane gap and some value of H. This is strongly expected from numerics and also analogy with the BBS model and everything. And I remarked that this boundary field is necessary because without that, we have, these gapless mode at boundaries. Okay. But anyway, with this assumption, basically the Haldane gap, with this assumption, I can prove that the index for the infinite volume limit of this Heisenberg chain is well defined, and it takes this non-trivial value -1. And let me prove this again. But again, the good news is that proof takes only 2 slides. Okay. So this is my finite chain model. And first of all, I say that this model, this Hamiltonian has a unique ground state, and it satisfies this. This means this is total SZ. So this says that the total SZ of this ground state is 1. Okay. And the proof is quite standard, and it's a linear algebra. You use the Perron-Frobenius argument. And this kind of, in the early days of quantum spin system, Elliott Leap and Mattis, they proved many theorems, basic theorems using techniques like Perron-Frobenius theorem. So this just follows this kind of standard argument. So if you're interested, I recommend reading my book that is explained there. Okay, so anyway, we have this. Then why don't we compute this limit of this expectation value, which is relevant to our index? So now I want to take alpha going to 0 limit, but of course, this is simply the same as putting alpha to 0. And what happens when alpha is 0? Alpha is this gradient. So if alpha is 0, this simply vanishes and this goes away, and theta is always pi. So this becomes this. But now this tells you that this part is 1. Okay. So this is simply e to the I pi, and you get -1. Okay. So this is what we found. We found that this is equal to -1. Is this our index? So this is our index. Okay. Are they the same? Well, actually not true. In this definition, I have to first take the L infinite limit and then let alpha go down to 0. And even in physics community, you're not allowed to exchange these two limits. Okay. But in this case, you can because of these two lemmas. Okay. Okay, so these two lemmas says that if your alpha is sufficiently small, this expectation value lives here or here for sufficiently large L. Okay, and then it lives here or here. But this tells you that in alpha going to 0 limit, it lives here. Okay, and then if you relax this limit and if you consider non-zero but finite alpha, then of course you can never be here. It changes only continuously, so you are here. You're certainly here. Okay, so you keep this finite non-zero but small alpha and take this limit, and of course you're still here, and then take alpha, the limit where alpha goes to 0, and of course you get -1. That was the proof. Okay, so what do you find from this theorem? Okay, so this is this finite system, and this is my assumption, non-trivial assumption. From this assumption, I could prove that index is -1. First of all, I'm not going to discuss the details, but this shows that there's a gapless edge excitation in the half-infinite chain model. So I was only considering finite chain, but you can consider half-infinite chain in which there is a boundary and it goes forever. Okay, And in this case, I have to assume I have to make an additional assumption about the uniqueness of the infinite volume Brown state. But anyway, with that assumption, I can prove that this model must have low energy excitation, which live near the boundary. Okay. But anyway, this is more important. This was our main topic. Okay. This has something to say about the existence of a ground state phase transition in this interpolating model that we have been discussing from part 1. Okay. And first of all, we already know that index for this trivial model is 1. If you accept this assumption, the Haldane conjecture, then we know rigorously that the index for in here is -1. So they are different. So my index theorem concludes that there must be something singular in between. So with this assumption, we conclude that there is a ground state phase transition in this interpolating Hamiltonian. And I'm not going to discuss this slide, but when I say there is a ground state phase transition, mathematically speaking, there are like 4 possibilities. But anyway, this is only here. But this is recorded, so you can pause and read this. Okay, so I relied on unproven assumption and made some claims, but actually there are several things that I can say without relying on any unproven assumptions. They're unconditional results. First of all, I would say that the spin 1 antiferromagnetic Heisenberg chain may have 1 topologically trivial unique gap ground state, topologically non-trivial unique gap ground state, or gapless or degenerate ground states. Well, this was total nonsense because these are exhaustive. Okay, so but what I have shown is that this first possibility, this is the most boring possibility, but this does not happen. Okay, so there are basically 3 possibilities, but I rigorously excluded this first possibility. And of course, we believe that this is a case. This is a case, and we want to exclude this, but we still don't know how to do that. But anyway, I could exclude this possibility. And also, this is, I think, interesting. There is something we can say about phase transition too. Okay, so suppose that the assumption, the Haldane conjecture, does not hold. Of course, we believe in it. Okay, not only because of the Nobel Prize, we believe in this Haldane conjecture. But suppose that it's not true, then this Heisenberg Hamiltonian should show something weird. Probably it's massless, or I don't know, exhibits spontaneous symmetry breaking, or anyway. So anyway, it's singular in some sense. Okay, so this means that if here you have trivial phase, and we know everything here. And if the assumption, the Haldane conjecture is true, we know there is a singular point. Okay, if Haldane conjecture is not true, then this guy itself is already this guy is singular. So there is a singular point here. Okay, so without making any unproven assumption, unconditionally, we can conclude that here, somewhere here between 0 and 1, something singular must happen. Okay, so I think this is conclusive. So this shows that there is at least one singular point, phase transition point, in this interpolating Hamiltonian. Okay, so here are some technical remarks important only for experts. So this is my finite chain Hamiltonian. And if you look at the symmetry, then actually this does not have all these 3 symmetries that you find in textbooks about SPT phases. So, and this was a bad news. And I still can only treat this specific Hamiltonian in my method. But Yohei Fuji saved my life, and they discovered this 4th symmetry, and this Hamiltonian satisfies this symmetry. Okay, and of course, in the infinite volume limit, all these symmetries should be restored, and we can make use of that. Okay, and I think some of you are interested in the Ogata index. This is the ultimate, most general index, which works for any symmetry classes that can host SPT phases. But unfortunately, this is difficult. So Yoshiko Ogata defined this by using operator algebraic language, and that is really, really necessary for her definition. So it's rather difficult. She constructs projective representation of the symmetry group by using some operator algebraic techniques. okay, and the split property and so on. And it's very hard to compute Ogata index. So we still do not know how to determine Ogata index for this Heisenberg Hamiltonian. Of course, you can do that. She could determine her index for like the BBS model by showing that it's the same as the Pullman-Turner Belk and Oshikawa index. But it's very hard for this thing. Okay, so this is a long summary for the part two. So we proved that the spin 1 antiferromagnetic Heisenberg chain has a non-trivial topological index. Whoa, this is great. But unfortunately, under the assumption that the model has a unique gap ground state, I had to assume the Haldane conjecture. But anyway, we rigorously ruled out the possibility that the model has a boring unique gap ground state that is topologically trivial. And also we established the existence of a phase transition in this interpolating model. And actually all these results extend to models with odd S. So not only 1, but 2, 3, and 5, and but not for 2, 4, 6, even thing. And I didn't say anything about this, but this is related to the very interesting discovery that was made by young Masaki Oshikawa back in 1992 about the fundamental difference between spin chains with odd spin and even spin. Okay, this is a very interesting topic, but I don't have any time to go into this. But anyway, to summarize here, let me stress that these were the first non-trivial rigorous results on topological properties of the antiferromagnetic Heisenberg chain, which I believe to be a realistic model, okay, not unlike the VBS model. Okay, so my time is running. So these are remaining issues. So I want to discuss relation with the Gata index of projective representation. I want to extend this to models with other symmetry, and this is related to a problem called the generalized Lipschutz matrix theorem, and also extend this to other systems. But let me discuss this big, heavy remaining issue. So we really want to justify the assumption, which is the Haldane conjecture, by developing a new strategy. Okay, this sounds crazy, but one thing we can imagine is find some computer-aided proof. I don't mean that we ask ChatGPT for a proof, but we invent some new finite size criterion which says like if you have this and this property for a finite chain of lengths like 100, for example, then our assumption for any L is valid. Okay, this is not totally stupid because we do have such a criterion, such criteria, if the Hamiltonian is frustration free. Okay, and of course, in this case, Heisenberg Hamiltonian is not frustration free, so this is very difficult problem. But I believe we should not give up. We should not give up. So I want to encourage all of you to join me and do not give up and think about this problem. Okay, so here's the final summary. So Haldane's discovery led to the valence-bond picture, matrix product state, tensor network, symmetry protected topological phases, and much more. But still, I want to emphasize that our understanding of the Heisenberg chain, where everything started, is still incomplete, and there still remains much more to learn. And I believe there must be more surprise to come in all directions. Okay, that's all. Thank you very much for your attention.
Thank you very much, Tasaki-san, for very great talk, including nice review of early days of Haldane gap conjectures. So we have a few minutes breaks before the Oshikawa-san's talk. If you have any question, could you put?
Can I ask one naive question?
Yeah.
So I would like to ask you about the index that you use to prove this theorem.
Yes.
So this is kind of very intuitively easy to understand. You have this twisting from
Yes.
0 to 2 pi
Yes.
gradually. But
Yes.
you can also generalize it to 0 to 4 pi or 0 to 6 pi. And can that kind of generalization give us something more non-trivial, or is it not very interesting?
Well, just you're just doing this on 1 more 2 pi, I think just sort of mean just doubles this. You mean
Uh-huh.
so I don't think you get anything else.
Okay, thank you.
Yeah,
And
but
yeah.
yeah, I think many of you are good at this kind of symmetry and transformation. So
Mhm.
yeah, I'm still asking if we can extend this to something much more sophisticated, not only U1 twist, but something more
Uh-huh.
Abelian or So
I
yeah,
see.
if you have any idea, I really welcome.
Okay. And another related question is about Ogata-san's index. Is
Yes.
it somehow related to your index or is it totally different?
Uh, Well, naively speaking, it looks totally different. You
Mhm.
have to have ground state which is with split property, and sometimes you consider von Neumann algebra that arises from ground state restricted on half infinite chain and so on, or you do some GNS and split property.
Mhm.
But of course, they coincide for the BBS model, the AKLT model, so they
Mhm.
must be the same. So that's one thing I'm discussing this with Yoshiko Gata, and one thing that I really want to do is to prove that they coincide in some cases. So I hope I can tell you more later.
So is it possible that they give different index,
I don't
different?
think so.
You
I
don't think so?
strongly believe that they are the same.
Okay, okay,
And I have very rough idea, but that's still very rough. But
okay.
my index is just this only gives you Z2, right?
Mhm.
And but Pullman Turner Bell Koshikawa index gives you something more like G3 if you have SU3,
Mhm.
AKLT model, and so on. Of course, Yoshiko's thing too, but mine always gives Z2. So
Mhm.
there are many things to think about. But when mine is defined, then I think it should be the same as Yoshiko's.
Mhm. I see. Thank you.
Thank you. Also, there's a question from public viewing, right? You Tokyo Physics.
Yeah.
Do I still have time for questions?
Yeah, one or two. We can accept 1 or 2 questions. So please.
Yeah, thank you very much. So I think I missed the explanation about why you could rule out the reason why Heisenberg model doesn't have unique gapped ground states, trivial ground states. Can you explain about it again?
Ah, okay. So that is basically my main theorem. So my main theorem says that you assume that the Heisenberg model has a unique gapped ground state. This is my assumption. Okay. With this assumption, there are 2 possibilities. This unique gap ground state is topologically trivial or topologically non-trivial. But with this assumption, I proved that my index takes this non-trivial value -1. Okay. So this concludes that it can never be the case that this is still true and it has trivial ground state, topologically trivial nature. Is that clear?
Yeah, I understood that the model doesn't never have only have 1 or -1, but I didn't understand why it's always -1.
Oh, that's my theorem. Okay. So that is something I proved. But in short, this is the answer. Okay. But this is too easy. But so I could compute.
Okay.
I could sort of compute this by using very elementary thing. But this computation is just trivial. Okay. But the main point is that the index is defined by this limit with this order. But I could only, this elementary technique just allows you to compute this thing. So I have to switch this order of limits. And that was that was non-trivial, but with two lemmas with these 2 lemmas, it was done.
Okay, thank you very much.
Ah, sure.
Okay, so now it's a time to move on to the Oscar-san's talk. So thank you very much, Tasaki-san, again.
Thank you very much.